Right, so as I said, we have lost a bit of time, therefore I'm trying to pull it back. So let us start first with the homework problem I gave you on the last lecture to check. I just want to make a few comments on it, not go into the details. And the problem was something like find integral from minus infinity to plus infinity of 1 over x to the 6 plus I dx. So that's what the problem boils down to. I just want to go over the main ideas because in case you get this kind of question in the exam, you need to know what to do. We won't be able to do it to the very end because we get angles that are not easy to realize as simple numbers. They're like cos 12, pi over 12 and stuff. We don't know it off by heart. But to solve such an integral, we can use the methods that we learned already, the residue theorem, and we can firstly find the poles. The poles are where the denominator is 0. In this case, you convert to z form, z to the 6 plus I equal to 0. You need to solve this. Find, there will be 6 roots of z. However, you shouldn't fall down off your chair and wonder what to do with 6 roots because you know that not all 6 roots are important. Only the roots that lie in the upper half of the game, upper half of the plane will be important because you will surround those three points with a contour. So let's now firstly see how do you find the roots, because I think this is the part that will confuse some students. You can write z to the power 6 equal to 0 minus 1i. Okay? If you had to plot 0 minus 1i, minus I is over here in the coordinate plane. Watch that carefully. That means that the angle theta is minus pi over 2. I'm using the negative version. You could call it 3 pi over 2 if you want in the positive direction, but I can use the negative one as well. And we know that z is e to the I theta to the power 6. So it's e to the I 6 theta equals to e. Here it's I and the angle is minus pi over 2, but this happens every 2k pi. So the z to the 6 is e to the I 6 theta. This point on the plane is represented by e to the I minus pi over 2. That's the angle. And of course, it happens every k pi, 2k pi. All right, so from this, you can then get that 6 theta is the same as minus pi over 2 plus 2k pi, which gives you theta being minus pi over 12 plus k pi over 6, dividing throughout by 12. So that gives you the 6 roots. So you have to take k equals to 0, 1, 0, 1, 2, 3, 4, 5. You take 6 numbers, 0, 1, 2, 3, 4, 5. That will give you all 6 roots. If you take 7, 8, 9, 10, you get the same roots again. It will cycle. So then, to work the roots out, let's take z0. Z0 will be when k is 0, so it's minus pi over 12. So you can say it will be cos minus pi over 12 plus I sine minus pi over 12. Z1, this time you use k equals to 1. So it's like having 1/6 minus 1/12, or 2/12 minus 1/12. Yeah, it's not supposed to be so. 2k divided by 6 is over 3, right? This is over 6. This should be k pi over 3. Do you hear that? I'm dividing throughout by 6 here. This is pi over 12. This is 2k over 6, which is k over 3. I knew something's wrong there. This is 3. Now it makes a difference. So I said k is 1. It's 1/3 minus 1/12. 1/3 is like 4/12. 4/12 minus 1/12 is 3/12, which is 1/4. So then you can say this is cos pi over 4 plus I sine pi over 4. Okay. Z1, Z2 will be cos of, now you have to put k equal to 2. It's 2/3 or 8/12. 8/12 minus 1/12 is 7/12. So we get 7/12 pi plus I sine 7/12 pi, and so on. Let me do Z3. It'll be cos of, when I put K is 3, it will be 3 thirds, 1, or 12/12. 12/12 minus 1/12 is 11/12. So I get 11/12 pi plus I sine 11/12 pi. Okay, and so on. There's two more, but I don't need them all. Now I plot these on a coordinate plane. You may be wondering, how do you plot that? Because you didn't work out the coordinates. Like, okay, this one is easy. Cos pi over 4 is 1/√2. This is 1/√2 into 1 plus I. That's easy to plot. But I can use the angles, guys. I can use the angles. For example, minus pi over 12 is minus 15 degrees. It's a ray in this direction here. And I stop at 1 unit. The radius is 1. So this point here is Z0. 15 degrees. This is minus pi over 12. Then pi over 4 is like 45 degrees, somewhere there. This will be Z1. What is the difference in the angle between those two? How many degrees apart are Z0 and Z1? 1, that's 45 degrees. That's 15 degrees. 45 plus 15 is 60. How many roots have we got? 6 roots, right? Did we not learn that the 6 roots of an equation distribute themselves on a circle, equally spaced? So if 6 points are distributed equally spaced in a circle, they will form an angle of 60 degrees between each pair. So likewise, this 15 plus 45 is 60. The next one will be another 60 degrees. So what is that? 45 plus 60 is 105. So there'll be another one somewhere there. But what's steeper than that? Let's make it steeper so it looks more realistic. 105 or something like that. That will be Z2. And the next one will be 105 plus 60, 165. So there'll be another one somewhere here. Z3. So, which are the relevant ones? There's going to be another one, Z4, somewhere here. That's 165 plus 60 is 225. Somewhere here, there'll be a Z4. And a Z5 will be 45, 15 plus 60 is 75, somewhere here. That will be a Z5. So those are the relevant 6 points, but we don't need all 6. You know, in this game, we have to take the upper half plane. So we surround the upper half, the upper 3, with a contour like this, a semicircular contour. We know that the integral of us on a semicircle is going to be 0, provided that the certain rules about the numerator having a degree 2 less than the denominator. So from minus r to plus r, if we do this, that's the integral we seek. So we only need the roots z1, z2, and z3. So then the answer will be the integral of 1 over x to the 6 plus I dx from minus infinity to plus infinity will be 2 pi I times the residue of 1 over z to the 6 plus I at z equals to z1 plus 2 pi I times the residue of 1 over z to the 6 plus I at z equals to z2 plus 2 pi I times the residue of 1 over z to the 6 plus I at z equals to z3. That's all that matters. Now, how do you find the residue? There's a simple theorem here which tells us we can differentiate the denominator. Differentiate the denominator, and so you will get, well, I think you can see 2 pi I appears all the time, so let me pull that out once and for all. So I should take the derivative 1 over 6z to the 5 and substitute the first point, z equals to z1. plus 1 over 6z to the 5, and substitute the second point, z equals z2, plus 1 over 6z to the 5, substitute the third point, z equals z3, etc. I'm not going to do it now because those points are not clear. It's like cos of minus 5 over 12 and stuff. They actually have values. They are special angles, but they are half of 30 degrees, so I can find their values. But it's a bit of a schlep to do that. So it's something I can leave. I just want to show you the idea. How do you find the poles? You plot the poles, you take the poles that lie in the upper half plane, and then you hit this formula, 2 pi I residue of them. How do you find the residues? Simple trick, in most cases, differentiate the denominator. And then that's it. Plug in those poles. And then you get the answers. In an exam, you wouldn't get crazy ones like that, where you have to plug in something very complicated. It'd be simple enough to plug in. All right, any questions on that? That type of stuff. You can practice the textbook one. The one in the book has got x to the 6 plus 1. That's a fancy one. I mean, anyone can do that. Real serious maths guys would put an I. Make it harder. Why make it easy? So that one, anyone can handle one. And it turns out one of the poles even lies on the y-axis. So yeah, it's a bit of a yawn. I won't do that one. You try it, practice it. It's a good exam type problem. You get these questions in the exam for 8 marks, 9 marks, 10 marks. It takes a lot of work. All right, now guys, we're going to switch on to the next aspect, next type of integral that we get, which is called the Fourier integral. Not the Fourier integral from the chapter 3, but a type of integral called a Fourier integral. It has a sine or cosine with it. I just want to discuss how you deal with that. But from here onwards, I'm not going to prove anything unless you deeply are interested in the proof. But time doesn't allow us to prove. Last year, if you look at last year's notes, I did proofs, but I don't think I'll be able to have enough time for that this semester's course. I proved something else last time, which I didn't prove last year. We'll keep changing it around. So this is what we call the Fourier integral, a Fourier type integral. Let's call it Fourier type integral. You know, Fourier has things like AK sine kx, AK cos kx. So when you have those combinations, then we call it a Fourier type integral. So the type is something like this: minus infinity to plus infinity, sum f of x sine kx or omega x dx, or integral of f of x cos omega x dx minus infinity to plus infinity. So these are interesting ones, where the f of x can even be a rational function. It can be some n of x over d of x. These are polynomials. Like you can have x sine x over x to the power 6 plus 1. If you don't have the sign, x over x to the 6 plus 1, then it's like the previous examples. But with the sin x now, the game changes for a cos x. So we need a new tool for that. Here, I'm going to state certain things and require an act of faith for you to believe them. But I think all the proofs are in the book anyway, so you should believe me. In some cases, if you don't believe me, then you read the proof in the book, and you can even ask me about it. I know the proofs, but it takes time to prove them. So we use this result here. Hey, this is shocking. So if you got n of x over d of x, let's say cos omega x dx plus I integral n of x over d of x sine omega x dx. This is the same as the integral of e to the ix I omega x, n of x over d of x, dx, and minus infinity to plus infinity everywhere. So if I want to work out something with the cos omega x, I work out this thing first. E to the minus, e to the I omega x times this. And now you see, I have done an example of this type in the last week, in the last lecture's example. There was e to the kx or something like that, divided by x squared plus 1 in all square or something like that. There was e to the power something. I think it was an example of that. And I argue that that one can be done with ordinary techniques because that's an entire function. And this is everywhere. The entire complex thing. So you can resolve this. And then, at the end of the day, if you want to solve a problem with the cosines, you just take the real part of that. If your equation or your question had a sign in it, you take the imaginary part of the answer you get. That's how you do it. You do the integral for each of the I omega x and take the real and the imaginary part separately. Okay, here we need that the integral along a semicircle is 0 if the degree of n is less than the degree of d. That's all we need here. You will recall in the previous setup, the degree of n had to be 2 less than the degree of d. Here we can make do just 1 less. That's because we now added a sine x term to it, or cos x term. It's not exactly the same anyway. So this is known as Jordan's lemma. This is not trivial. This is known as, this thing is shocking me. Known as Jordan's lemma. Why would it be shocking me when there's no electricity? Okay, Jordan's lemma. So, so we can write, we can get. This is how we work the integral out. The integral of minus infinity to plus infinity, sum n of x over d of x, e to the I omega x dx. How do we work this out? It's 2 pi I residue of n of z e to the I omega z over d of z. You work the residue at the poles, z equals to z k or whatever. If necessary, you have to sum them if there are more than one pole involved. So just to recap, I said that if you got a Fourier type integral with a cos omega x and a sine omega x, you don't work with that. You work with this. You work this problem out. Treat it as e to the I omega x. That can be worked out using this residue. Then you go back. If the question has cos in it, you read out the answer with the real part. If the question had a sine in it, yeah, then you read the answer with the imaginary part, the I part, coefficient. That's how you get the answer. Well, let's take an example. I won't take the example from the book, so you can work it on it yourself. But let me take one of the tough examples, which are not prescribed. So find minus infinity to plus infinity. This is x sine x over x squared plus 4x plus 20 dx. I hope you agree that these integrals can't be done with ordinary calculus. If you can think of a way to do this with ordinary calculus, let me know. They are far more complicated than the ordinary first year calculus substitutions and stuff. Like if you had x sine x, then you were in business. You can hit that integration by parts and stuff like that. But now you're dividing by this heavy term here. Changes the picture. Well, I won't stop you from trying integration by parts. Let this part be u. Let that be dv. You try it and see if you get anywhere with it. I doubt you'll go far with it. But why must I dash your spirits? Try it. Now let's follow this strategy here. You can see that we have this guy sitting here, sine x. So it's a Fourier type integral. It means that I must deal with x e to the ix. So to solve this, we consider integral minus infinity to plus infinity x e to the I x over x squared plus 4x plus 20. Right? At the end of the game, because I want sine, the imaginary part will be the answer I seek. So you can say the poles where the denominator is 0 will be where z squared, we convert to z now. Z squared plus 4z plus 20 is 0. The first problem is to work the poles out. What are the poles going to be? Well, there's several ways to do this. You can hit this with the quadratic formula if you like. You can then hit it with the Moivre's theorem if you like. Sometimes you can see some simple methods like this is like z plus 2 squared plus 4, that's plus 16, so 4 squared, 0. You can see it. Then you can say z plus 2 squared equals to minus 16, so it's plus minus 4i. Z is equal to minus 2 plus minus 4i. So there are two roots. Obviously, it's a quadratic. You plot these two roots, and you check which one lies in the upper half plane. That's the one that's in the game. The other one is not. So the 2 points are minus 2 plus 4. Minus 2 plus 4, it will be somewhere here. Minus 2 plus 4. Other one will be minus 2 minus 4, somewhere here. That's out of the game. So then it follows that we throw around this a semicircle like that. Contour, because we know the integral along this circle here, semicircle is 0. I appeal to Jordan's lemma. I just mentioned that Jordan's lemma. I said Jordan's lemma handles that integral when the degree of the numerator is smaller than the degree of the denominator. It doesn't have to be too smaller. You know, a difference of 2 or more, as we said last time. It even works when the difference is 1. That requires a proof, but that proof is what I'm not going to now. It takes time. So, you can then say that solution integral of minus infinity to plus infinity of z e to the I z over z squared plus 4z plus 20 dz is 2 pi I residue of z e to the I z over z squared plus 4z plus 20. And I am working out the answer at minus 2 plus 4i. I'm only working the answer out here, minus 2, 4, not here. So to work out the residue, there is a neat trick for this also, 2 pi I. The trick is you have f of z over the derivative of the denominator, 2z plus 4. And I plug in z equals to minus 2 plus 4i. Right now I plug in minus 2 plus 4i and carry out the substitutions, and hopefully everything will work out nicely. So 2 pi I times z will be minus 2 plus 4i e to the I z minus 2 plus 4i all upon 2z will be minus 4 plus 8i plus 4. I'm just doing the substitutions now. Let's do that. That will become 2 pi I in 2. Let's leave the minus 2 plus 4i as it is. Right, e to the power. This will be minus 2i. Then you got 4i squared. 4i squared is minus 4. 4i squared is minus 4. So it's e to the minus 4 times e to the minus 2i. At the bottom, minus 4 and plus 4 kill each other, and you get 8i. Right, so now we are almost ready to end this. It's 2 pi I. The i's will cancel off, of course. 2 goes here 4 times. The pi is still there. Pi into. So 4 goes into the top thing there. It will be minus 1 plus 2i all upon 2. E to the minus 4. And e to the minus 2i, isn't that cos of minus 2 plus I sine minus 2? That will be cos of minus 2 plus I sine minus 2. Radians, that is. So this can be pi over 2 e to the minus 4 minus 1 plus 2i into cos 2 minus I sine 2. You see, I need to separate the real part and the imaginary part. That's where I have to get to. Then because my question has got a sign in it, I'll read the imaginary coefficient as the answer. So I still got a little work to do now to combine the imaginaries. So far it's pi over 2 e to the minus 4. When I open this bracket out, it will be minus cos 2i times minus I. That's minus 2i squared. That's plus 2 sine 2. Now, we do the imaginary part. It will be 2 cos 2 plus sine 2. Okay. So I have now fixed up what I need. So now I must read off the imaginary part, this thing here. Just the yellow part times the stuff here. That will be the answer for the integral that I see. So therefore, the integral of x sine x over, what is this expression? X sine x over x squared plus 4x plus 20 dx minus infinity to plus infinity will be the imaginary part of the above. The imaginary part will simply be pi over 2 e to the minus 4 into 2 cos 2 plus sine 2. Of course, if the question had a cosine in it, then I'll read this part. Pi over 2 e to the minus 4 times this side. Either way, the answer is a real number. Notice the answer is a real number. The integral we see is some real number. Pi is a real number, e is a real number, e to the minus 4 is a real number, cos 2 radians is a real number, sine 2 radians is a real number. The integral is a real number. I'll bet you cannot get this integral in another way. Can you integrate this in some other method? And look at how elegant this method is, the residue theorem. We didn't have to do integration by parts or any heavy lifting. You just have to substitute stuff. The hardest piece of work here was to differentiate the denominator, you could say. Other than that, it was just applying the theorem. Any questions? That is the correct answer. 5 over 2 to the 4, 2 cos 2 plus 9. Yeah, that's right. All right, that's an important type of integral, the Fourier type integral. We're going to meet that integral in chapter 3, which I will start tomorrow. One last type of integral is the principal value integral. Let me just drop that down. Now I'll start with the principal value. So far we have had integral of n of x over d of x, and now we can even have a sine and cosine stuck in there as well, dx. But thus far we have dealt with d of x having complex roots only. And they are obviously going to be in pairs, because complex roots appear in pairs, conjugate pairs. So there will be an even number of brackets. Then of course, the next important question to ask is, what if you have like a real root, like a z minus 2 or something sitting there? How come you left that out? That was a more important one. I mean, that's the easier one, you would say. So we plunged into the complex one for a purpose, because we had to establish the way the residue theorem works. You'll find that with the real valued roots, the same method works, except that you take half of it. So now, again, a bit of hand waving here to motivate this without having to go into details. So if you just consider, let's take an integral like sine x over x dx, minus infinity to plus infinity. We can show, and we're not going to go into the details, we can show that this converges, which means that you can find this integral. And can even write the integral of sine x over x dx minus infinity to plus infinity is the integral from minus infinity to infinity, the imaginary part of e to the ix over x. Because we know that sine is the imaginary part of e to the ix. Now, the question arises, can I take the imaginary sign outside? Can I interchange imaginary with integral? The answer is no. So, strictly speaking, we cannot. So we cannot swap integral and imaginary. In fact, imaginary part of, if I take the imaginary part of e to the ix over x dx, this is meaningless, since we will have imaginary part of the integral of cos x over x plus I sine x over x dx from minus infinity to plus infinity. And it is known that integral of cos x over x dx diverges. So then this presents a problem. How do you handle a thing of this type? You can't switch imaginary and integral. That's the thing here. So therefore, again, this is a bit of faith here. Maybe I'm like a faith healer now. just telling the story instead of just proving it, because we don't have time to prove. But we then consider what we call the principal value of the integral. The principal value. The basic result goes like this. Under some circumstances, we can do it. If we know the function is convergent, we can do the swap. And the basic result is this. If a real pole exists, example, z equals 2 or something, not z equals to 2i, or 2 plus I. A real pole is z equals to 2. Then the integral from minus infinity to plus infinity of f dz is 2 pi I residue of f at z equals to z naught plus 1 pi I residue of f at z equals to z za, where za is real. So this is the normal complex part. Complex zeros. This part here is for real zeros. I'll give you a brief synopsis of how the proof goes. Now, it is something like this. So here we have the familiar, so you have a root. Okay, you have some root on the top. Okay? We only need the ones that are in the upper half plane. Then you have one guy who lies exactly on the x-axis. That's a real pole. The other two are complex poles. So the trick is, you surround these guys by a contour, but you do it in a more sly, cunning way. You do a contour like that. The integral there is okay, it's going to be 0. And those two guys on top are fine. Then you come here, and then you surround this guy by a smaller semicircle. And carry on your merry way. You use a radius of epsilon. So now the thing is that this was a neat trick to avoid this bad guy here. Why is this sitting on the x-axis? It should be on top. Game is easy. 2 pi I residue at each of the points, and we sum them up. Now this guy here is lying on the x-axis, presents a problem to us. So we bypass him with a very small circle. Again, the integral along the circle here will be 0. Let's call it d. That will be 0. Integral c of radius r is 0. Okay, let's put epsilon. Radius epsilon is 0. And then what's more is that we make the epsilon shrink, become as small as possible. But we still keep this point z a outside. But we shrink it, we make it so small that it's almost like inside. So basically, it becomes part of the game. And you'll notice that while we have 2 pi I there, here we have 1 pi I. Here we have 2 pi I, and here we have 1 pi. It's like saying this point z is half in and half out. It belongs to the contour and the. That's really the argument that we use to prove. We have to still prove a lot of things. But this is the basic result. Business as usual, 2 pi I residue f. The pole that lies on the x-axis is equal to 1 pi I. That's it. That's all the problem. I haven't done justice to it. I just told you the result. I feel a little guilty, but we haven't got the time to go into details. In any case, the details may bore you to death. It's in the book, and I won't go into the absolute final point. Let's take an example. Usually, an example will make the thing clearer. So again, let me not take the textbook example because you may want to read it yourself. So here, example, find the integral of minus infinity to plus infinity 3 sine pi x over x cubed minus 1 dx. It's very similar to the textbook one, but not exactly the same. Textbook one has got a plus x cubed plus 1. It changes again. It's not exactly the same thing. The roots of the cubic could be different. Well, the first thing we do is we inspect that and we see how there's a sign. It's like a Fourier. So then we take 3e to the I pi x. We work with that problem and read off the complex coefficient. So we consider the integral of 3e to the I pi x. Well, let's put z over z cubed minus 1 dz. You don't even need the 3 for now. Later on, you can bring the 3 into the game. The 3 is a coefficient of sine. Okay, so let's now talk about the poles. The poles are z cubed minus 1 equal to 0. You can hit this with the Mohr's theorem, as I've done before. 3 theta equals to whatever. Or you can factorize this, man. I think you know from high school what are the factors of the difference of two cubes. Z minus 1 into z squared plus z plus 1. You learned that in high school, how to factorize the difference of two cubes. So then z equals 1, and that's the bad guy there. That's the real root. There's no I in it. Or z equals to, hit this with the quadratic formula, minus 1 plus minus root of b squared minus 4ac. 1 minus 4 is minus 3 for 2a. So that's minus 1 plus minus root 3I over 2. So those are the three roots of 1. Two complex roots as expected and one real root. If you had to plot them on a plane, so z equals to 1 will be there. Then minus 1 plus root 3 over 2, or minus half plus root 3 over 2. It will be somewhere here, right? This will be minus half minus, no, plus root 3 over 2. And down here would be minus half minus root 3 over 2. So those are the 3 points. You plot the 3 roots. The coordinates are minus half root 3 over 2, minus half minus root 3. X and Y coordinates. Plot them on the complex plane. Again, diagram if you like. Then we throw a contour over the upper half plane, as we've been doing all the time now. So, and of course, you come here and skip this guy and go there. Those moves are not really vital because now you can just apply the result. So then we can say integral is equal to 2 pi I residue of 3e to the I pi z over z cubed minus 1 at the point z equals to minus half plus root 3 over 2i. Oh, it's a light. We use black. Plus pi I residue of 3e to the I pi z over z cubed minus 1, this time at z equals to 1. Okay, so z equals to 1 has got is a real root, so that guy takes a pi I. The other complex roots have 2 pi I, and we only deal with one of them. The other one lies outside the game. We only worry about upper half of the plane. They appear in conjugate pairs. They are mirror images of each other. So now to work out the residue, that's 2 pi I. Okay, so we can differentiate the denominator, 3 e to the I pi z over z 3z squared, and I substitute minus half plus root 3 over 2I. Plus likewise pi I, same story there, 3 e to the I z, I pi z that is, over 3z squared. This time I plug in z equals to 1. Okay, the numbers are a bit nasty, but not too bad. Well, the 3's cancel off there. So we get 2 pi I. E to the I pi. E to the I pi. Z is minus half plus 3 over 2 I. Over z squared is minus half plus root 3 over 2 I squared. That's pi I. This one is quite harmless. E to the I pi over z squared is 1. So this means we have to finish this problem. That's 2 pi I. Okay, this one is e to the what's e to the minus half pi I times e to the minus root 3 over 2 pi. At the bottom, if you square these two, what do you get? 1/4 plus 3/4. No. So it will be 1/4 minus 3/4, minus 2/4, which is minus half. In the middle, you'll have plus 2 of those. It's minus 1. It's minus root 3 over 2 I. Let's check if that's right. Right? Plus here, pi I. E to the I pi is cos pi plus I sine pi. It's 2 pi I over, or into, e to the minus half pi I is cos minus pi over 2 plus I sine minus pi over 2. E to the minus root 3 over 2 pi, which is just a number, over minus half plus root 3 over 2 I. And this side here, cos of pi is negative 1, so it's minus pi I. That at least is sensible. Cos sine pi is 0. Let's look at the ugly business of sorting this out. You still need to know which is the real part and the complex part. In other words, you can't abandon this problem here and get tired, leave, and go home. You have to finish it. So it's 2 pi I. Let me put the minus outside. Minus 2 pi I. Okay, this e to the minus root 3 over 2 pi, that's a number. Cos minus pi over 2. What's cos of pi over 2? 0, right? Hey, yeah, then we business. Cos of pi over 2 is 0. That's okay. Sine over minus sine pi over 2 is minus 1. It's minus I there. Aha. Minus I. And then multiply the top and bottom by the conjugate. Half minus root 3 over 2I. The bottom you'll have half plus root 3 over 2I times half minus root 3 over 2I. Minus pi I. Okay, let's plug on. Let's see what happens here. There's another minus here, so it becomes back 2 pi I e to the minus root 3 over 2 pi. This thing becomes, well, why don't I say I squared is minus 1. Let's put that there. So this is simply half minus root 3 over 2i. And at the bottom, it'll be a squared plus b squared. 1/4 plus 3/4, which is 1. Minus pi I. It is coming down to a sensible number, guys. In case you're getting worried this is becoming ridiculous. Multiply this by half. 2 pi squared is minus 2 times half minus 1. So it's minus pi e to the minus root 3 over 2 pi. Minus the minus, well, well, this is minus 1. I squared is minus 1. So it's minus 2. That cancels there. It becomes plus root 3 pi e to the minus root 3 over 2 pi. Okay. Minus pi I. That's it. So the integral I seek to get 3 sine pi x over x cubed minus 1 dx minus infinity plus infinity is going to be the imaginary part of the above. That will be, so there's an I here, it will be root 3 pi e to the minus root 3 over 2 pi minus pi. So, as dirty as it looks, that's the answer. If this question of cosine pi x, then you read the other stuff. This will be the answer. Minus pi e to the minus root 3 over 2 pi. Okay, I hope you have much respect for this method. It's quite a stunning technique. Although it's quite, complicated here to calculate these final things. But the actual game, the heart of the problem is above, right? You do realize that the heart of the problem is here. This residue theorem. The problem is solved here. That's the real punch. This is donkey work plugging it in. This should be a cool head and working on the final result. I don't call that thinking work, that's donkey work. Or dog work, as some people say. If you have any questions, feel free to ask. There's not too many people here, so you don't have to feel lousy if the question is not great. That's what happens with people in a big class. They hesitate to answer questions or to participate. The good news is that the last problem is very easy. Yeah, that is the last one. I want one more. It's rather easy. Or you'll also see in the textbook for the principal value, I just carried on using it like a normal integral, but they put a dash on the integral, like this here. That means principal value. It means that we're taking the liberty to swap the image, the imaginary part with the integral. It's not legal generally. If the integrand is convergent, it may be possible, which is the case in all these examples here. But I haven't really seen this all the time. You can leave it out too if you want. So the last one is the easiest one. I know what you're thinking. That's what he says all the time. But it never is easy. This one, I promise you, would be. And this is an important result. The integral from minus infinity to plus infinity of sine omega x over x dx. What's the answer for this? Have a guess. What do you think? 0, infinite, I, pi, 1, perhaps? Limit of sine x over x, we know as x goes to infinity is 1. So do you think that the answer will turn out to be 1 here? It's an intriguing question. I don't think you'll guess the answer. The answer is a one number thing. It's one of the big numbers, pi, e, or pi. What do you think? Have a wild guess. Well, it can't be I, because you don't expect the area underneath the sine x over x graph to be an imaginary number. It's between pi and e. Well, let's see. Note, firstly, an old concept, integrand is analytic everywhere. Why? Or how do we know this? Well, look, we've been assuming all the functions we're dealing with are analytic everywhere. But it's a point that we need to investigate at first to see whether we are dealing with something that's analytic everywhere, or if there's some points that need to be removed. Well, because if you take sine x over x, isn't sine x minus x cubed over 3 factorial plus x to the 5 over 5 factorial plus blah blah blah, or minus blah blah blah? And if I divide that by x, that's a Fourier, the Taylor series. Divided by x, it'll become 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6 over 7 factorial and so on. It's analytic. Has a Taylor expansion. That's valid everywhere. There's no points you need to exclude. There's no dividing by x because x goes into x. X goes into x cubed. X goes into x to the 5. So there's no, x doesn't spoil again. Right, now, so we've cleared that up, which is an important side issue. So we can take the integral of sine omega x over x dx minus infinity to plus infinity. Because I want to be able to swap the imaginary with the integral, I'll use a principal sign here for correctness. I'll just change nothing, but put the dash dx. So this allows me to say imaginary part of the integral of e to the I omega x dx over x. So the only pole that we have here is z equals to naught. Notice there was a bit of a trade-off here, a loss. I said sine x over x has no pole. There's no pole. There's nothing that's positive because you can divide into x divides into all those guys. But when I go into e, this has got 1 plus x squared over 2 factorial, 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. The over x will still be in the game. There will be a pole. You'll be dividing by 0. Or dividing by x. So now there is a pole. Z equals to naught. Okay, and there's only one pole. Z equals to naught. Surround this pole by contour. Like that. And then hit this with the residue theorem. So the integral of e to the I omega z over z dz from minus infinity to plus infinity is pi I. It's a real pole. There's only one pi I. Residue of e to the I omega z over z at z equals to naught. That's pi I. Differentiate denominator, it's e to the I omega z over 1. And you plug in z equals to naught. So the answer is pi I. Right? But not over yet. It's never over. Until you're thinking it, but you don't want to say it. I didn't say that. You said it. I say horizontally disadvantaged. That's a more politically correct phrase. So we need the imaginary part, guys. We are dealing with sine. So the integral from minus infinity to infinity of sine omega x over x dx will be the imaginary part of the above. And the imaginary part is pi. So the answer is pi. The integral of sine x over x as you go to infinity on both sides is pi. What kind of a function is sine x over x? Odd or even? Do you know the shape of the sine x over x function? Or it's also called sinc x. Sine x over x has a short form sinc x. S-I-N-C. But firstly, answer my question, is it odd or even? What can you say about sine? That's odd. X, that's odd. Odd over odd. What can you say about odd over odd? Like x to the 7 over x to the power 3. It's x to the 4, so it's going to be even. So sine x over x, which we call sinc x, is even. And if you draw sine x over x, at 0 it's 1, eh? It'll be like that. That's sine x over x. Y equals to sinc x. This is 1. We know this from first year calculus. The limit as x approaches 0 of sine x over x is 1. Notice the symmetry, because I know it's even. So we are saying that the area underneath that graph is going to be pi. If you add up all these bits and pieces below it, all these parts here, believe it or not, they will all add up to pi. They don't kill each other, they double. Because it's an even function, you see, they don't become 0. Had it been an odd function, yes, they'll kill each other. But you add up all those bits, some positive, some negative, add them up to infinity, I promise you the answer will be pi. That's the answer, you discover it. It's quite incredible, right? That you can do this. Now, just to summarize this last result, which is a useful result in chapter 3. We can say the integral of sine omega x over x dx from minus infinity to plus infinity is pi, provided omega is positive. In the instance when omega is 0, then you will be having sine 0 over x. So 0. It will be 0. Remember, it's not the x that's 0, it's omega that's 0. And in the instance when omega is negative, sine of the negative x, isn't that minus sine x? in the fourth quadrant, sine of negative x is minus sine x. So in the case of negative omega, this would be minus pi. So that's how the integral of sine x over x behaves, pi or minus pi or 0. Right, guys, so that's where I conclude the lectures for chapter 2. Covering all types of integrals, complex analysis, Cauchy-Integral theorem. Residue theorem was the highlight, and then it had all these subtypes. That's what you're going to practice for the exam. So tomorrow I'll start chapter 3. Normally we need about Thursday. I'm still going to be around. I managed to get a flight that's after the lecture. The game is long on Thursday, and then we have a period. We'll see about Monday whether it's a TAT or a lecture, but we still have a Tuesday and a Thursday period. We finish on the 17th, right? Lectures end 17th. So I'll broadcast the lectures anyway, so if you miss it, you'll have the broadcast. Okay, so the rest